Thanks, Mark. Right, so good afternoon, everyone. My name is Bleakley. I'm offering manager for modelling MBS solutions within IBM. But basically, my history is I've been doing model-based systems engineering for probably about 25 years in various forms. And it's only really, and I've seen it really take off in the last probably about 10 years. I'm also heavily involved with things like OMG, which is Object Management Group. There's a lot of people here from that. But what I'm really going to talk to you today is about this idea of how we can use the digital twin. What is the digital twin? How we can tie it into simulation and AI. And really, a lot of it's about model-based systems engineering. Okay? So, in terms of the problems that we're facing, I think everyone's very familiar with these. People want to get to market quicker, with higher quality, with better products. With things like IoT, that's changing. Okay? With IoT, the things that we're developing are actually starting to become more connected. They're becoming more connected to the engineering and the development life cycle. And it leads down to, I think, there's some really interesting talks we've already had today, especially that MBSE squared one, about engineering, the engineering life cycle and the development life cycle. That needs to be engineered into your MBSE products, into the products themselves now, when you start to look at what we're doing with IoT. Also, the other thing that's driving this initiative that's come out over the past 2 years, DoD, Digital Engineering Initiative. I think there's a talk about this later on this week. This is something that's been talked about probably for about 4 or 5 years in various forms, but it's only really started to take off in the last 2 years. But we've seen a big increase in people's understanding about what a digital thread is, what a digital twin is, and how they actually relate to each other and how they relate to the engineering life cycle. And this is becoming more and more evident. And we're getting more and more questions about how do I do this? Because the DoD has been very good at saying, this is what you should be doing. Now we're getting the question of, how do we do it? Tell us how do we do it? And the DoD going, we don't know. So that's why they come and see people like me and various colleagues. So in terms of the digital twin, it works in various different areas. So part of it's about, go back a step. Part of it's about how you working with your engineering for the different products. Okay, there's a lot of a digital twin going on within the products themselves, but it's also how they connect to the wider domains, and also how you're working with these cyber-physical systems, doing the simulation for these artifacts, so you can do the virtual representations. And really the thing that drives all this and brings it all together is the Internet of Things. It's how you feed back information from the things that are being built into the things that are part of your development process, and why this is really important. And this is also where there's a lot of leverage, or there's a lot of gain that you can get from employing these different types of models in different ways and starting to improve your development process. So this is a definition. I'm not quite sure where this came from, but certainly within IBM, there's been a lot of different definitions of what people think of as digital twin. They think of it as just the representation of the life cycle data, how that works, as it's a virtual representation of the thing being produced. Other people see it as being the CAD data. Okay, other people see it as being, in my world, a lot of it comes down to the engineering analysis. But this definition brings together two very important factors. The first off is the virtual stateful representation of the product and system, and then you've got the and it's across the life cycle operational real-time data. Okay? So this is bringing not only together your engineering data, your engineering world, but it's also bringing across your model or your physical thing, okay, and how you feed back that information. This leads back to the ideas that we had earlier on about this MBSE squared, and about how your engineering process needs to be as architected as the thing that you're architecting, but now it's becoming even more important because then they need to be architected together to support one another. The next part of this, breaking it down, is about this dynamic recalibration for improved decision making. This is the feedback of the information that you're getting from the product that you're producing so that you can improve it later on. And this is becoming more and more evident in the standards that we're seeing. Things like ISO 26262, which is used in automotive, functional safety. There's part of that called operations. The operations part is about feeding back information into development of our life cycle. So, digital twin is a bit of a journey. So we can look at it in different ways. This was brought up a little bit earlier, but we can look upon it as being as designed. This is the virtual representations of the elements. It can be the CAD drawings, it can be the simulation models, 3D CAD, finite element analysis, systems design type, MBSE, traditional, well, model-based SE that we've been developing with. And then looking at how it ends up being built, simulation models of how the production systems, and then how it's maintained with prediction, augmented reality, all that information being fed back to the physical object using real-life data. And what we're getting on the left-hand side is the virtual prototypes, productions, and then services. Okay? So this is tying all that information together. And a big role of this is the simulation, and it might be how we use AI as part of this. In terms of implementing this digital thread, I think you hear a lot about it in this environment. Basically, we use OSLC. So for parts of our tool chain, we have analysis and design tools, workflow management tools, test management, requirements management tools, all linked together using OSLC. But this isn't, we're not just talking about this from the perspective of our tools. These need to be open, okay? They need to link into a load of other third-party tools. Again, going back to this idea that you need to architect your development systems as well as the systems that you develop, or the systems that you develop, ultimately. So how do we tie into testing tools? How do we tie into electronic design, other simulation tools, product line engineering tools, PLM tools, okay? And the way that we do that is through OSLC. But the interesting part to this, which is where the real digital twin lies for me, it's in this thing that we call the lifecycle query graph, or lifecycle query engine. It's basically a graph of all the information that exists, all the linkages that exist between all these artifacts, okay? This is one of the real benefits of digitization and tying all this information together. Because when you have that, you start to see the gaps in your information. And if you're really good, you start to see the real impact analysis and what happens when you do change. When we first started doing this with our demo models across some of these artifacts, we realized how bad they were, how few big holes we had in them. And we had to really start to build our models to be a lot more complex to show the full picture. But this is an implementation of a digital thread that came from a customer of ours. So that's what people's view of it is, load of connected nodes and edges. But really, it's about the information that's spread across the different tools. So we've got a workflow tool on the left. It's managing, I think it's picked out from this task to implement a certain feature. Then the requirements that have been connected to it, the subsystem requirements, leads down to models, and it leads to tests, okay? And all of this needs to be managed in the context of what we call a global configuration. These all need to be set at the same version, okay? And so we're managing things in concert with one another. One of the areas where we can actually start to use the AI on this is to actually understand the relationships that exist between all these different elements. Okay, there was the example of using NLU to create models. That's something we tried a few years ago, and it's amazing with a half-decent, even with the basic NLU model that we had, we managed to get a sensible model out of a 60-page document in like 2 minutes. Okay, so I was really pleased to hear someone's been playing with that. But part of it is we can go back. Not quick enough. But part of it is definitely about using the patterns, understanding the textual language that sits between all the different requirements, and maybe even deriving test cases from this so we can use AI to actually understand these linkages between the different different parts of the life cycle. Also, when we build a model, as soon as we start to put blocks on a diagram, start to connect them together with connectors or dependencies or information flows or ports, we are building a digital model, okay? That then gets reflected into the architectures themselves. So the other part, or the part where most people think a digital twin is, it's around the simulation of 3D CAD. So this is basically a running model, simulatable model, but we can also have bits that map to things like FMI, FMU, continuous type models that come from Simulink. We can work out graphs from them. But also apart from just doing it at this level, we can use this information to maybe start understanding behaviors and abstracting behaviors that end up being represented as algorithms developed from machine learning. This is sort of like a slightly bigger picture of that, whereby we're looking at hybrid simulations, bringing in FMIs, U's, mapping them together with architecture, mapping them to hardware in the loop components, and starting to map everything together and bring it in as a virtual simulation. The next thing is, how do we work with this thing called a digital shadow? Digital shadow is the data that's created from the thing that's being produced. And when we have that information, we can start to do a whole bunch of other new tricks. So with the IoT, we feed that information into a database. We can start to feed it, or we can start to take the inputs from that, or the environmental inputs to that, feed it into the engineering world, do a comparison of the IoT data from the vehicle, or from the plane in this instance, against the simulation data, and start to do a comparison, okay? When you have that, you can start to optimize your product. You can find faults in your product as well, okay? And also, you may be able to update your engineering model, okay? So it can be used in a number of different ways. The other thing is, by using that information from the vehicle, we can actually start to do machine learning. We can start to build algorithms that can start to work with the system to understand how it actually works and how it should behave as well. This is the sort of environment that you need to deal with that. So this is our sort of rough architecture for it. So up here we've got like our general engineering applications, linked to PLM, mechanical CAD, mapped onto the knowledge graph, and then various assets down there which push into machine learning, and then it can all sit on the cloud, basically. Okay? In terms of how this fits with a more simpler view of the world, going back to block diagrams, because we all understand block diagrams, this is your basic systems design. Any system consists of a user, some sort of control algorithm, some sort of physical components that push information into an environment that affects what we're doing. Okay? And it should also feed back into the user as well. When we start to map that into how we might improve it for AI and use it within systems and software and hardware development, we can take these two parts and we can feed information from those into our database, map it onto the digital twin. If we see any errors coming into it, that pushes it into the development process. Okay? So this is where the comparison goes on that I was talking about earlier on. And this can happen at multiple levels. And it's the reason why you've now got to think about your interfaces from your system and how they actually integrate with your development process into your engineering directly. And it leads to much more engineering. You've got to think about those interfaces and that architecture. And then as we end up doing changes within our development process, how do we actually deliver those into the system? Okay? It's much harder to deliver a change into a physical component than it is into a virtual component. And this is sort of one of the areas where Tesla has got its edge because it's doing over-the-air updates. I think this is about the only company that's doing that at the moment. But that's an important edge that they have, that they can deal with that. The other interesting thing about this is when we look at this, that virtual digital twin can also be replaced by a machine learning algorithm that we might have developed from the inputs and the outputs and the reactions from the user. Yeah, and that's also, that development process has not only got to feed back into the systems that we're developing, but it's also got to feed back into the virtual digital twin as well. So you've got to make changes in multiple places. So this is a very small example. It's a demo model that we use to demonstrate some of this. This is based upon an example that we used in a project in Europe called Crystal. The idea was that there was some sort of, there was an algorithm, or there's a turboprop plane, I think, in the original one, but it was about rear wing de-icing. And they needed to be able to break the ice off the front wing, the leading edge. So it was how do we monitor that and how do we understand what's going on there and make the changes to it to determine what's going wrong. Come on. So the idea was that we have some sort of sensor in the wing, it's monitoring the wing, and if the temperature in the wing gets too high or too low, it then sets an error. All the information from that is fed back to the engineering system. And then we can monitor that information, and we can generate a failure request on it, maybe do some fixes on it, and then actually identify where the problem is, and then do the fix and send it back out into the real world. And the way that we do that is through our engineering platform, but it's also tied into the IoT. So we have assets that can monitor information that's coming from the plane. And depending upon the various inputs and outputs of what's going on, so in this instance we have the plane, it's sending information back to the IoT platform. Okay, temperature, generates a warning when it goes up too high or too low. That generates an issue in our development process. That can then either be monitored through the digital thread to do the change impact analysis, or one of the later demos that we've got, we've actually tying this directly into the models, and we're doing a comparison between the model and the actual physical thing itself, so we can see where that error might occur. So it's running things in concert or in parallel. And when we have that change analysis, we can work out all the affected parts within the system from, well, in terms of all the requirements, all the way down to the bits in the model, down to the elements in the BOM and the PLM assembly as well. So it's really covering all aspects of the system. But this is what we mean by when we're trying to tie the digital thread to the digital twin together. So in summary, really, to enable this digital twin, it really requires the implementation of a digital thread. And when you've got that digital thread, you can do a whole lot more, you can do a whole lot of stuff with it. I mean, we've just got two things up there, which is impact of change and root cause analysis. But once you start seeing that information, you start to see big potential to see large gaps in your data, to see where you've gone too deeply into your design, all sorts of different things. It helps drive this root cause analysis. That digital twin is really used to reveal the failures in the system. By using that digital shadow, we can either use it by comparing the real information or into various model constraints or requirements. And from there, we can start to actually also use predictive fault analysis. So if you have a digital twin there, and you feed it with the inputs from your system, okay, you're comparing it to what's going on in the real world, to what you think should be going on, you can do some predictive fault analysis on it as well. Again, that's another application for machine learning and AI. Also, machine learning really used to represent the physical and behavioral systems models, although this is very dependent upon the learning data being captured. And you need to capture the environment data as well, okay, and the user data. There's a lot more than just, it's not as simple as the way that we look at building a cyber-physical system in terms of just looking at the constrained system, the system is much larger in terms of the information that you've got to gather. At the moment, I think this is one of the next stages that we need to look at and start to work with. And finally, the final point is your engineering really becomes an integrated part of your product lifecycle and your product. They've really got to be architected together to work together. And I think that was borne out. I mean, there's been really good presentations, and I connected with all of them at some level, but it was that MBSE squared one that really worked for me, and it really supports some of the things I've been talking about here. So thank you very much.